These mixture problems seem to be one of the more difficult tasks of this unit. So when we look at this one, it's asking how much NS. Now remember, NS is just normal saline or neutral solution, basically sterile water, would you add to 240 milliliters of an 18% solution to dilute it down to 15%. So what we're mixing here, the NS is 0%, and we have our 18% solution. So that is what we are mixing. And we are trying to get a result of 15%. The volumes that we have 240 milliliters of the 18%. We can let X be either one of either the 0 or the 15%, but we're asked how much of the NS, so how much of the 0%. So I'm going to let that be X so that the result of our variable is the answer to our question. So if that's X milliliters of 0% and 240 milliliters of 18%, then when we combine them, we have X plus 240 is the amount of our 15%. So 0% is just 0 times X. 18% is 0.18 times 240. That's going to equal 15% is 0.15 times X plus 240. 0x, of course, just cancels out, disappears, nothing to do with that. 0.18 times 240 is 43.2. Bless you. On the other side, we've got 0.15 times x is 0.15x. And 0.15 times 24 is 36. So our next step, we will subtract the 36. That leaves us with 7.2 here equals 0.15x. And finally, we will divide by the 0.15. So 48. So x equals 48. Let's go back up and make sure we know what that means. That's 48. That's volume. All my other volumes are in milliliters, so that's 48 milliliters. So we would add 48 milliliters of sterile water to that solution to dilute it to 15%. Any questions? Did anybody have that one? Did you get it right? Oh, a few of you? Good. Okay. Okay, so today we're going to shift gears a little bit. The last topic we need to get out of the way in Unit 2 so that we're ready for our dosage calculations in Unit 3. Of course, this is finishing up Unit 2, so we will be looking at starting next week with Unit 2 tests. Just like Unit 1 test, usually we try to complete that in the first hour. Generally, we don't get it done in the first hour. It takes about an hour and 15 minutes, hour and 20 minutes. So we only have about 30 minutes or so to 25 to 30 minutes to start our new material at the end of the class. And what we'll usually do is about a half an hour into class next week, we'll see how everybody's doing and see how the time is, and we'll make a decision then if we're going to have time to do a short lecture before we're done with that class or not. After this, generally, after the Unit 2, the other tests generally do take the full 2 hours, so we don't try to squeeze in a lecture after the other tests. Okay, so our last topic, we want to start looking at the measurements and the units. A little bit of background on measurement. Measurement came from a need to communicate. Like length, for example, if, let's say, two people are trying to build stuff they're identical. If they're in the same room together, it's easy enough to do. They can just walk over and mark things off from each other and work on it. But if they're down the hall or across town or any sort of distance, they have to have some way to communicate that back and forth. Now, you could always, cut a string or cut something to the right length and send that back and forth. But it'd be really nice to be able to record a size, write it down, and then just send a piece of paper with a bunch of these measurements, these sizes written down so that you can record them that way. And also from the viewpoint of consistency, it'd be nice to be able to record them so that next time you build one, you can make it exactly the same. So you don't have to have it sitting in front of you to copy. And that's where measurement came from. So when they went to measure things, for example, like this piece of paper, they might say, okay, I'm going to take a pen and I'm just going to go, that's 1, 2, that piece of paper is about 2.5 pens long. I'm making a big assumption though when I do that. If I send you a note saying, okay, you need to cut that at 2.5 pens long, my assumption is you might have this pen. So you go 1, 2, well, 2.5 pens for you is much longer than it was for me. So I'm making two assumptions. One is that you have a pen, and even if you do have a pen, that they're the same size. You can see these are very different in size, so trying to compare measurements with the two of them just isn't going to work. It's going to be very different. So they chose things, one, that pretty much everybody had, and two, that was relatively close to the same size from one person to the next. For length, they actually started out, can anybody tell me what our smallest unit of length is in our standard measuring system? You know it, you're just not. About that long? An inch. The inch came from, it was the distance from the end of your thumb to the point of that first knuckle. Now you might be thinking, well, people got different size fingers. Well, the fingers themselves tend to vary a lot in size, but the thumb is not. It's relatively consistent. So from one person to the next, they could measure with their thumb and get a decent consistency from one piece to the next. So they went up there, they had the thumb for an inch. The next biggest unit we use is a foot. Literally the distance from the tip of your big toe to the back of your heel. That was 12 inches. Bigger than a foot, they tend to use a yard. Now, a lot of people mistakenly think a yard is the length of your stride. And the length of your stride is approximately a yard, but that's not where it came from. The yard was actually a tailor's measurement. It was the distance from your outstretched arm to either the center of your chest or the tip of your nose, depending on which part of the region you lived in, but it comes out to be the same length pretty much. Now, all in a yard is about 3 feet. Now, all of these units varied a little bit from one person to the next, and also 12 inches, each foot did not contain 12 inches. What happened was in about the 500s, King Edward declared that his thumb and his foot and his yard were going to be the official units that everybody was going to use. And so they came in and they cut little pieces of wood the size of his thumb and his foot and whatever, and they passed those around. They made copies of those and passed them around for everybody to use. And even though it was a very egotistic move on King Edward's part, it really opened up measurement. Because up until that point, if I wanted to measure this piece of paper, well, I'd take my thumb and go 1, 2, 3. It was very slow because I had to sit there and count. And also there was a lot of error because every time I moved my thumb up a notch, I'm not necessarily getting it exactly where it ended the time before. So by King Edward doing that, they had these little blocks that were cut to that size. Well, then they just started, if they wanted to measure an object, let's say this is the object we wanted to measure, they realized very quickly that, hey, rather than just taking that block and moving it along, I can take a stick, and I can set my block on it, and I can mark on that stick with some sort of whatever, a scribe or a pencil or whatever, and then I can just mark the stick and number it, and now rather than having to move that little block and count it, I can just hold that stick up next to it and I can read off the number. And that was the beginning of rulers and measuring as we know it today. And excuse me. From there, of course, we started dividing up the units into halves and quarters and whatever. If this were more of a construction-based class, we'd go into that development more. But for the medical fields, it isn't that important. But that standardization, King Edward declaring that his thumb and his foot and everything were going to be used, was really opened us up to huge advancements in how we do our measurement. Now, even for King Edward, his foot did not contain 12 of his inches. It was about 150 years later, after he was dead, that they adjusted those lengths. They decided, hey, if I measure that table in feet and you measure something in inches, it'd be nice to be able to compare to see which one was bigger or smaller. Up until that point, there was no way to compare from one unit to the next. So if you measure it in feet and I measure it in inches, one of us has to go back and remeasure it so that we can compare. So they adjusted the sizes to make it 12 inches in a foot. Obviously, it was close to 12 inches in a foot. Otherwise, they wouldn't have chosen 12 to force it to be that. But that's the reason why the numbers are so awkward in our standard measuring system, is they were taking units that were never designed to go together, and they adjusted them so that they did fit together. The metric system, of course, that's standard. And standard measuring system, I always say that it was a developed or evolved measuring system. So as it was needed, it was adjusted to make changes to fit what was needed. It was kind of forced to work together. The metric system is actually a lot older than most people think. The metric system was developed in the 1880s and 1890s. So it's been around for about 130 years now. The metric system was a created measurement system. And that's a big deal because they had been using different measurement in different forms for literally millenniums, for thousands of years. And they knew all the weaknesses of the standard measuring system, and they knew all the strengths of the standard measurement. They knew what they liked about it, they knew what they didn't like. So they were able to create the metric system to keep those things that worked well, but then change those things that didn't work well. The biggest thing they wanted to change was having 12 inches in a foot, 3 feet in a yard, those awkward numbers of conversions from one unit to the next. So the metric system, everything was based on tens. Because everything was based on tens, and our numbering system, the place values of our numbering system are also based on tens, the conversions within the metric system ended up being based on just moving decimal points. So we'll come back to that more in a little bit. Let's take a look more at specific units. So let's talk about volume. And actually, we're really not talking about volume. I should say it's capacity that we're talking about. A little note on volume and capacity. Volume is measured by measuring 3 length dimensions. So what do I mean by that? Well, if I have a box and I measure that it is 12 inches in this direction and 7 inches in this direction and 6 inches in this direction, the volume of that box is 12 inches times 7 inches times 6 inches, otherwise known as, 504 inches cubed, cubic inches. That's volume. It's length dimensions that are multiplied together to create the volume, the space within that object. Capacity does not require length. It is just a set size, a set amount. And our standard capacity, one of our main units that we use is called a cup. A cup is literally your cupped hand. You hold your hand down like this and you dump powder, usually sugar or flour, is made for baking mostly. So it was dry powdered measure. What you could hold in your hand was a cup. It was one cupped hand. was what that was really stood for. Now, of course, we've standardized those and we've made measuring cups, and so we can do fluid measure with them as well. But originally, that was not intended for fluid measure. A little bit larger, that was meant for both fluid and powdered, was a gallon. 1 gallon was actually about the size of the standard men's hat. Now, I'm not talking about a cowboy hat. I'm talking about, the derby hats that were commonly worn, like dress hats. Those held about 1 gallon. You might have heard the phrase or the term 10-gallon hat. That wasn't a hat that held 10 gallons. It was just a really big hat. It was a figure of speech. So smaller than a gallon, we have a quart. Can anybody tell me how many quarts are in a gallon? 4. The word quart is actually from the word quarter. It is a quarter gallon. It's not a unit in itself. It's actually just a division of a gallon. Smaller than a quart is a pint. Now, a pint, again, was a unit on its own. A pint was actually a standard drinking serving glass. There are 2 pints in a quart, and those are units that had to be adjusted to fit together. The quart and gallon went together because the quart was defined off the gallon. The pint was adjusted to fit in with them. Smaller than a pint, then is our cup. And again, the pint and the cup were never intended to work together. The pint, the gallon, the quart, and the pint were fluid measure. They were measuring liquids. The cup was dry measure. So again, they adjusted it to fit it together so it works with both. And there are 2 cups in 1 pint. Smaller than a cup is fluid ounces. So we're back to putting a liquid measure in with our dry measure. Can anybody tell me how many fluid ounces are in a cup? 8. Perfect. Smaller than a fluid ounce is a tablespoon. Now, if you're like me, I memorized how many tablespoons were in a cup, not how many tablespoons were in a fluid ounce. So can anybody tell me either one? There are 16 tablespoons in a cup. There are 2 tablespoons in a fluid ounce. Smaller than a tablespoon is teaspoon. Anybody remember how many teaspoons are in a tablespoon? That one is 3 teaspoons in a tablespoon. A little bit of a side note here before I continue. The abbreviation for tablespoon, you saw I abbreviated it capital TBSP. I use that abbreviation because that is the clearest one for me. But other abbreviations, it's sometimes done with a small t, BSP, sometimes just a capital TSP, or sometimes just a capital T. All 4 of those are acceptable abbreviations, are used abbreviations for tablespoon. Teaspoon, it is either small TSP or just a small t. So you can see the potential for confusion here. TSP can be used for either one. All that separates them is a small t or a capital T. And the same with just T. Trust me, if you're making a batch of cookies and the recipe calls for 3 teaspoons and you mess up and do 3 tablespoons of salt, I haven't thrown away too much cookie batter in my life, but that one had to go in the garbage. Anyway, for this class, that's as small as we're going to go, but I'm going to throw a couple more out there. You don't have to write these down. The only reason I throw them out there is they're units you have heard, and a lot of people don't realize they actually are standard units. Smaller than a teaspoon, you have 1 teaspoon is 2 dashes. A dash actually comes from a spice shaker. You think of a salt shaker. Our salt shakers are actually very, very small compared to a traditional spice shaker or salt shaker. The spice shakers were a lot bigger and had bigger holes in them. And a dash was just literally one turn and dash, like one shake of the salt shaker. That was a dash. Smaller than a dash, 1 dash contained 3 pinches. A pinch was exactly what you think. You put your fingers in there, pinch them together, and what's between your fingers, that's how much spice you throw in to the recipe. And 1 pinch, I'll probably spell this wrong, is 2 smidgens. The smidgen is the one that always kind of grossed me out a little bit. The smidgen is you stick your finger in there, and whatever sticks to your finger, you put that into the thing, which the cook with really sweaty fingers has big smidgens. I don't know. Okay. Now there are units that are larger, like a bushel. A bushel is 8 gallons. A peck is, I can't remember if it's 2 gallons or 4 gallons. I believe a peck is 2 gallons. It's 4 pecks in a bushel. You still see pecks. I mean, you hear bushels all the time when they talk about grain production, price per bushel. You will still see pecks. If you go buy strawberries, you have those crates. They have 1 peck and 2 peck crates of strawberries. That's where those come from. 1 peck is 2 gallons. So that is our standard units of volume. I want to take a look. We'll come back to metric here in just a little bit. I want to take a look now at weight and mass. Just like volume and capacity, and I should have said those are standard units of capacity, not volume. I always mess that one up. Just like capacity and volume, there is a subtle difference between weight and mass. But we do tend to just ignore that difference and use them interchangeably. Weight is the force of gravity pulling on an object. Mass is defined to be the amount of matter in an object. Literally, how much material, how many particles are within that object. The difference really is how they're measured. Weight is measured by a scale. And what a scale is it's some sort of a spring, some sort of flexible material. A spring is set up so that the more you stretch it, the longer it stretches, the more force it takes to continue stretching it. So a scale is you have a spring set up, then you have an indicator that's attached to that spring, like so. And when you hang your weight to the bottom of that, it stretches the spring, and that indicator then moves according to how far that string stretches. The further the string stretches, the heavier that object is. Mass is measured with what's called a balance. So you have the object we're trying to measure on one side, and on the other side, we use known masses until it balances. And when the two balance, then that is whatever this mass is, this known mass is here, is the mass of the object we're trying to measure. Now you might be looking at that thinking, well, both of them are involving gravity. What's the difference? Well, the difference is if you go somewhere where the gravity is different, let's say you go to the moon. On the moon, since gravity is 1/6 the gravity it is on Earth, that spring is going to stretch less. So if it started out here, this is 0. Instead of stretching all the way down to here, it's only going to stretch about 1/6 the amount. The force of gravity is less, the weight is less. With a balance on the moon, yes, what gravity is pulling on the object is going to be less, but what gravity pulls on the known mass is also less. So mass will not change depending on the gravity that you're in. So mass stays the same. Mass is constant. Weight depends on gravity. On Earth, gravity is relatively consistent. If we're dealing with a standard system, it is the metric system, I should say, it's 9.8 meters per second squared. It's an acceleration. Is the average force of gravity on Earth. It does change slightly at the equator, especially if you're at a higher elevation on the equator. It gets down to about 9.68. At the poles, it gets up to about 10.02. So gravity is slightly more at the North and South Pole than it is at the equator. But it's close enough to the same that we tend to just use mass and weight interchangeably. We assume gravity is a constant and we don't worry about the difference. Put it this way, a 200-pound person, if they went from the North Pole to the equator, they might notice a difference of maybe 8 or 9 pounds in their weight because of the difference in the force of gravity. So it's less, it's about a 4% difference is really all it comes out to be. Okay, so let's look at standard units here. And for standard units, we tend to focus on weight. There is a unit of mass in the standard measuring system that most people have never heard of, and it is called a slug. 1 slug of mass is about 32 pounds. You ever heard the phrase, well, there's a whole slug of them out there? That's where that comes from. It's actually a unit of mass. We're going to be measuring, if we're using the standard measuring system, we're going to be using weight. And we're going to start from the largest ones and work our way down again. Our largest unit of weight, of course, is a ton. Hopefully in the medical field, you don't have to use that one too much. Just saying. 1 ton, our next smallest unit is the pound. 1 ton is 2,000 pounds. Now, to be specific here, that is actually what is referred to as a net ton, or sometimes called a short ton. So if there's one that's called a net or short ton, there implies there's something out there called a gross or long ton, and there is. The difference is the ton was originally created for buying and selling grain. Well, you couldn't put a ton of grain on a scale. It would just fall off. So you had to have a container that you put it in. So a gross ton was the grain plus the container. And the container that they used was about 240 pounds. I'm not going to write this down because I don't want to confuse you. Everything we do in this class, a ton would be 2,000 pounds. But there is something out there called a gross ton that is 2,240 pounds. And that is the grain with its container. So then smaller than a pound. By the way, the abbreviation for a pound is LB. The reason for that, LB comes from the Latin word for pound, which is libra. It would make sense to use PD as the abbreviation for pound, but in the bookkeeping system they had for buying and selling grain, PD was already used as the abbreviation for paid. So in order to keep from confusing the two, they used the Latin word libra for pound, and so use LB for the abbreviation. Smaller than a pound, we have, what's next down the list? Ounces. 1 pound contains 16 ounces. For abbreviating ounces, we also use the Latin word. I can't remember what the Latin word for ounce is right now, but it abbreviates OZ. Smaller than an ounce. This one sounds metric, but it's not, is a dram. 1 ounce contains 16 drams. And now, depending on whether we are dealing with dry measure or wet measure, because fluid measure and dry measure became very, very different. We're going to stick with dry measure right now. In our dry measurement of weight, there's a smaller unit than a dram, which is called a grain. 1 pound, it's defined off a pound instead of off of smaller units, is 7,000 grains. Grains are used a lot for, if you're into hunting and gunpowder for guns and stuff like that, size of bullets and things like that. It was also one of the original apothecary units for measuring medication. Grain was actually a standard size, like a grain of salt. You actually count out grain by grain, which you can imagine how tedious that would be to measure medication like that. A dram was often used for prescribing medication. And they might prescribe 1/8 of a dram or 1/4 of a dram for certain things. So that is dry weight. Before I talk about wet weight or liquid weight, I want to mention something. Again, this is not going to be something you'll be tested on, but you hear a lot about precious metals. You know, that gold has gone up to $1,700 an ounce or whatever. When they're talking about gold and silver and platinum and other precious metals that you might invest in, they are not talking about regular pounds and regular ounces. And we talked about King Edward declaring that his thumb and foot and everything were going to be the official measurements. Unfortunately, he was not the only ruler that had that same idea. At different times and in different regions, different rulers declared that their thumb or whatever was going to be the official measurement. So there are actually different feet out there. That was one of the big weaknesses with the standard system, is from one country to the next, a foot was not the same thing. And a pound was not, bless you, a pound was not the same thing either. So they were very different from one to another. Precious metals, the center for buying and selling precious metals was for a long, long time the island of Troy in the Mediterranean Sea, just off the coast of Greece. So when we're looking at buying and selling precious metals, we are looking at troy measure. So we're looking at 1 troy pound. And 1 troy pound is about 0.82 of our standard pounds. Our standard US pound, I should say. 1 troy pound contains not 16, but 12 troy ounces. So a troy pound, you can see, is slightly smaller than our American standard pound. The troy ounce is slightly larger than our US ounce. Again, I won't test you on that, but you hear those phrases enough that it's good to throw them out there. Well, if I want to look at liquid measure, we talked about fluid ounces as being a measure of capacity. 1 cup containing 8 fluid ounces. Smaller than a fluid ounce, of course. It would make sense to have a fluid dram. The abbreviation for dram, by the way, is DR. The problem is, in the weight system, 1 ounce is 16 drams. In the fluid measuring system, 1 fluid ounce is only 8 fluid drams. And then there is another unit for apothecary, for medical units. 1 fluid dram contains 60 minims. Minim, as you can imagine, comes from the same root word as minute. It was very common in different measurements to use that same root word. So 60 minimums is just like 60 minutes. The biggest thing to remember is that it comes off of fluid drams. So we have all these standard units, and you can see it's very, very cluttered and muddled because they just took units that were being used and tried to cram them together to make a measuring system. If we look at converting from one unit to another, it can be tricky because you have to remember all those conversions. And as we mentioned, they developed the metric system to try to eliminate some of that issue. So in the metric system, some of the issues they addressed, the first one is only one unit for each type of measuring. What does that mean? Well, in the standard measuring system for measuring length, we had inches, we had feet, we had yards, we have rods, we have miles. In the metric system, the only unit of length is the meter. For weight in the standard system, well, for weight or mass, we have pounds, ounces, drams. In the metric system, they have grams for mass. In the standard system, we had gallons and quarts and pints for measuring capacity. In the metric system, there's liters, period. Only one unit for each type of measurement. And then the second thing they did was all conversions were powers of 10. So if we had, if we had to measure something smaller than the standard unit, in the metric system, they use prefixes to divide that unit up. And that division is always going to be either dividing it up by 10 or multiplying it by 10 to get a bigger unit. So let's take a look. In the metric system, let's first define our standard units. We're going to define our unit of length. The unit of length is a meter, abbreviated with just an M. A meter is about 39.29 inches, slightly larger than our yard. Now, I've asked this question for years before I actually finally got an answer. Why didn't they make the meter equal to a yard? It would have been so much easier if they just made the meter equal to a yard, and then we could, convert back and forth a little bit quicker. Well, like I mentioned a few minutes ago, from one country to the next, from one region around the world to the next, different leaders declared, their measurements. The yard is very, very different from one area to the next. The metric system was developed in Switzerland, and the meter is actually equal to the Swiss yard. So unfortunately, it wasn't our yard that got chosen there. For capacity, they use a liter. Now, the liter, I was always taught, when I was in school, you abbreviated the liter with a capital L all the time. The reason that I was taught that was back at that time, the 1 and the small l looked almost identical. In fact, if you go back before my time, the old typewriters, a lot of the old typewriters didn't even have a 1 key on them. You used a small l for 1. So if I had something like this, you don't want to leave that question, is that 51 or is it 5 liters? If I use a capital L, that's obvious that that's 5 liters. So that was the purpose for telling us that you had to use a capital L. Now with most of our modern computer fonts, the small l and the 1 are distinguishable, they're distinct. So it is okay to use a small l to abbreviate liters now. You'll see me most likely use the capital L all the time just because it's what I'm used to. Now then, we talked about mass and weight. I'm going to mention weight first. This is a unit that doesn't get used much, at least not in standard practice. In science and engineering, it's used quite a bit. The unit of weight in the metric system is a Newton. The abbreviation is just a capital N, but we don't need to know that because we're not going to use newtons in here. 1 kilogram is about 9.8 newtons. Then, of course, mass is what we tend to use more of in the metric system. The unit of mass is a gram, and that is abbreviated with just a G. A gram is about the size of a large paper clip. Is about the mass of a gram. Now, there are connections between these. That was another one of the weaknesses in the standard measuring system is 1 gallon in our standard system. 1 gallon is approximately, not even equal to, I have to use a little curvy equal sign there because it's not exactly equal to, approximately 231 cubic inches. And 1 gallon is approximately, it's like 8.1 pounds of water, and so on. The conversions between units are very, very ugly. So that was one of the other things they wanted to address in the metric system was those issues. 1 milliliter, and we'll look at the prefix milli after a bit, is defined to be 1 cubic centimeter. So 1 milliliter is literally 1 centimeter by 1 centimeter by 1 centimeter in size. This comes in handy way more often than you might think. If you look at like calculating even your car engine, you might say it's a 3.0 liter or 3.4 liter engine. They can take the measurements in centimeters, calculate the volume of the cylinders, and then that volume very quickly, let's say that they calculate it out and it is a 3,200 cubic centimeters of displacement. Well, 3,200 cubic centimeters is, since 1 centimeter cubed is 1 milliliter, that's 3,200 milliliters. And as we're going to see in just a little bit, the conversion from milliliters to liters, that's just 3.2 liters. Very, very quick and easy conversions from one unit to the next. So, oh, by the way, liter, don't be shocked if you see it spelt that way. They do the same with meter, just not as often. L-I-T-R-E is the European spelling of liter, and it is starting to catch on here. Okay, so let's take a look now at these prefixes. So we've got our gram, our meter, our liter, our standard units that we use for measurement. If I need to measure something that's smaller, we use prefixes that make them smaller. So the prefix deci means 1/10. So like a decimeter would be abbreviated DM like that. That is 1/10 of a meter. Deciliter, 1/10 of a liter. Smaller yet is centi. Centi means 1/100th. So a centigram would be CG, or centimeter would be CM. It'd be 100th of a gram, or 100th of a meter. Next is milli. Milli is 1/1000th. So milliliter would be ml. It's 1,000th of a liter. As we keep going smaller, you can see here they went dividing by tens. Every 10, tenths, hundredths, thousandths, had a prefix defined for it. As they kept going, they didn't name like the 10,000th or the 100,000th. They skipped down to the millionth. Millionth was micro. The abbreviation for micro, since the small m was already used for milli, the abbreviation, the official abbreviation for micro is the Greek letter mu. So like a microgram is mu g. I'll write it a little bit bigger up here. It looks like that. It looks like you can think of either a P where the top doesn't close or a U that has a long tail in front of it. Now, the medical field was one of the first fields that entered all of their data into the computer. All their information started being entered into a computer. There is no mu key on the computer. So in the medical field, they adopted their own abbreviation for micro, which is MC. So MCG would be a microgram, or MCL would be a microliter. And again, they didn't go, the 10 millionths and 100 millionths they didn't do. They did skip down to a billionth. Which is a nano. We're not going to get down to anything that small in this course. That's why I put it off up to the corner like that. But you heard, actually, in the last couple of years, you haven't heard about it near as much. But a few years ago, you heard about a lot nanotechnology, nanoscience. And all that really is, a nanometer is a billionth of a meter. In other words, you take a millimeter, which is about the width of your pencil lead, and you cut that into a million pieces. That's what a nanometer is. A nanometer is basically getting down to the size of a single atom. So what nanotechnology was designing things from single atoms, assembling them from the atoms on up instead of the other direction. And this has come into the medical field. There's a lot of nanotechnology is used in medications. There are nanomers, they call them. It's a molecule that they use for medications that they actually have a pill. They have pills out there that will release different medications at different times. They actually assemble the pills in such a way that, maybe a painkiller is released first, and then a medication that does something else that you need the painkiller to mask. And so it releases, not only do they have the time release medications, it'll slowly release the same medication slowly over time. They actually have those nanomers that will release, it'll actually change what medication it is releasing depending on how long it's been since it's been put into the body. So anyway, as we go the other direction, if we wanted to measure something larger than a meter or larger than a gram, we have deca. The abbreviation deca means 10. Now, since D was taken for deci, they use DAL or DAM or DAG for decaliter, decagram, decameter. That would be 10 liters or 10 grams. Hecto is 100. So a hectometer would be 100 meters. It's HM. Kilo is 1,000. So a kilometer is 1,000 meters. Just like going the other direction, they went 10, 100, 1,000, then they stopped. They didn't do an abbreviation for 10,000. They didn't name the 100,000 either. They skipped to the million. The abbreviation for million is mega. You'll notice I put a capital M on mega because small m was used for micro, or for milli. The mu was used for micro. They use capital M for mega. So a megagram is a million grams. It's not relevant necessarily for medical math, but a megagram is actually what they call a metric ton. It's 1,000 kilograms or a million grams. Now they designed this system and then they put it into use. And once they put it into use, they realized the main units got used, obviously, grams, meters, and liters. But all these other ones in between didn't get used much. In fact, deca and hecto don't get used hardly at all. The only use of either of those I see is hecto sometimes gets used in land surveying. They use hectometers and hectares. It's kind of, the R is like the equivalent of an acre. But kilo gets used a lot. Kilometers, kilograms, not so much kiloliters. A kiloliter would be like 270 gallons. But the kilo gets used quite a bit. In fact, in some cases, they don't even acknowledge the hecto and the deca anymore. On the other side, same thing. Really, the milli became used as the main units, and the deci and the centi didn't get used hardly at all. Micro does get used a lot in the medical fields because you need to have smaller dosages of medication. So a microgram or a microliter gets used quite often there. Now in the United States, the centimeter gets used a lot because it's the closest unit to an inch, and the inch was so ingrained into our habits that to switch it, just draw us into the metric system, the centimeter got used quite a bit more because that's the scale that we're used to measuring in. If you go into European countries and a lot of other countries, the millimeter gets used way more than the centimeter. Also in the medical fields, deci does get used. A deciliter gets used often on most of your blood tests. If you do a cholesterol test and it tests a 180, that's 180 milligrams of, what is it, triglycerides or whatever, cholesterol molecules per deciliter of blood. Or if you do a blood sugar test and you get a 75, that's 75 milligrams of blood glucose per deciliter of blood is what that test is indicating. Okay, it's time for a break, so let's take a break, and when we come back, we'll look at converting between these units.